How are suspension bridges protected from earthquakes? Imagine a bridge that can sway with the ground shaking beneath it, rather than breaking apart. That's the goal of modern engineering when it comes to keeping suspension bridges safe during earthquakes. These structures are marvels of human achievement, but they face the challenge of seismic activity in many parts of the world. To meet this challenge, engineers have developed a variety of techniques that help these bridges absorb and dissipate the energy from earthquakes. One of the key methods involves using seismic isolation bearings. These are special devices placed between the bridge's foundation and its approach spans. They are made from layers of steel and rubber bonded together with a lead core. These bearings allow the bridge to move or rock gently during an earthquake, reducing the amount of force transferred from the ground. This movement can cut seismic forces by up to 67%, protecting the main structure from damage. Another important strategy is strengthening the critical parts of the bridge. Engineers retrofit towers, cables, and anchorages by upgrading materials or adding extra bracing. This reinforcement helps these components resist the stresses caused by seismic waves. For example, adding steel braces or improving connections can make a big difference in how well the bridge holds up during a quake. Design flexibility also plays a major role. Suspension bridges are naturally flexible because of their main cables and suspenders. These elements can bend and stretch, helping to spread out seismic energy instead of concentrating it in one spot. The towers and anchorages are built to move with the seismic forces without cracking or collapsing. The steel cables form a parabolic curve that acts like a shock absorber, distributing dynamic loads evenly. Modern suspension bridges also include aerodynamic shapes and damping systems. These features help prevent vibrations caused by wind or seismic activity from building up. Damping systems work like shock absorbers in a car, absorbing oscillations and keeping the bridge stable. Historically, innovations like seismic isolators have been added to some of the world's most famous bridges. The Golden Gate Bridge in San Francisco was retrofitted with seismic isolation bearings at its approaches, greatly improving its earthquake resilience. The Akashi Kaikyo Bridge in Japan, one of the longest suspension bridges in the world, was designed with advanced seismic features to withstand the strong earthquakes common in the region. All these measures work together to protect suspension bridges from earthquakes. They combine the natural flexibility of the design with modern technology to absorb shocks and prevent damage. These innovations mark important steps in engineering, allowing these record-breaking structures to span vast distances safely in areas prone to seismic activity. They show how human ingenuity continues to push the limits of what we can build and protect.